Hi everyone, and welcome back. Today we're going to look at stoichiometric calculations involving gases. You may have already looked at some of these. I'm just going to take you through the number of examples that are provided in your textbook and talk through the different things that point out that we need to understand when doing these calculations. And then of course there'll be more questions available for you to practice these skills. So let's get started. You'll remember from when we did mass stoichiometry and even volume stoichiometry in year 11 that what we're talking about is the ratio of moles of reactants and products, which means we always need a balanced chemical equation. Okay, so in the case of what we've been looking at so far in Unit 3, this could be a thermochemical equation. When we're talking about gases, it is definitely probably going to be a combustion equation if we're linking this back to fuels. We have to pay careful attention to our coefficients so that we know the stoichiometric ratio of these reactants and products. And it's important to remember that in any equation, we are still bound by the law of conservation of mass, which means the mass of all reactants must equal the mass of all products. And with anything in chemistry, we must also pay attention to states. That's going to be critical when we're talking about gas stoichiometry, because a lot of the times you need to pay attention to what is a gaseous product when it's formed for some of the questions. So this one here this equation is essentially showing us the reaction for the combustion of methane. It's complete combustion because we have CO2 and H2O being formed. And this shows us that for every 1 mole of methane, 2 mole of O2 will be burnt, and then we will produce 1 mole of CO2 and 2 moles of water. So the ratio here between the fuel and the CO2 is a 1:1 ratio. So if we know we've burnt all the fuel, if we were going to work out how much CO2 was formed, we know it'll be the same number of mole. And then we can work out any other component in the reaction as well. Looking at this, it is important to remember that in this case, all of these states are gases, which means that we could use our gas equations for these reactions. Okay, this is our first example. So we're working with chapter 3, and as I said before, this one is in your textbook. This one is simply asking us to work out how many moles of carbon dioxide are generated. So this is saying formed, so we know CO2 is going to be one of the products, when 24 moles of propane. So in this case, they've given us what propane is, but you should remember from organic that prop means 3 carbons, ane means all single bonds, so this would be CnH2n plus 2 for our rule, because this is an alkane, so we would have C3H8 as the formula, which is what the question has told us. So remember to practice this as you come across organic names. Always take the opportunity to practice writing your molecular formulas and your names as you come into contact with them. And we've been told it's burned completely, so this is saying complete combustion. Okay, in oxygen. So we know that the oxygen's likely to be in excess. So because we've got complete combustion and we've been told we're burning all 24 moles of propane. So as I said before, the first step that we're going to have to do with any of these is write a balanced equation. So we have C3H8, gas, because remember things burn in the gaseous form, and this is less than 4 carbons long, so it will be a gas under standard conditions. Plus O2 gives us CO2 and H2O. We would start by taking our carbon from the fuel. Always start with our carbon for combustion reactions. Will give us 3 CO2. Then we take the number of hydrogens, divide by 2 and put that in front of our waters, which would be 4. Then we just double check that all our oxygens are okay. So in this case we have 4 oxygens plus 6 oxygens, which means we need a total of 10 oxygen atoms, so we need 5 lots of O2. So this one is correct and it is balanced. Once we've done that, we need to know the number of mole of the known substance. In this case, that's propane, and the question has told us that it's 24 mole. So this is from the question. And then we need to work out the ratio for what we're looking for. The question wants us to work out how many mole of carbon dioxide. This is our unknown here. So if you may remember, we want to multiply by a ratio of what we want, which is the CO2, over what we know, which is the propane. So this gives us our 3/1 ratio. If you're using the ratio grid, you may be setting it up this way, where we have C3H8 is to CO2. We use our coefficients, so this is 1 is to 3, and then we know this is 24 is to X. And then in this case, we're going to cross multiply. X is going to be equal to 24 times 3, which works out exactly the same as the way that we did over here, where we get the 3:1 ratio. So we're going to take that 3:1 ratio and multiply by the number of mole of the known, and that gives us 72 mole of CO2 will be produced. Okay, so what I want you to do now is I want you to read this question, pause the video, have a go at doing it yourself, and then come back and go through my working if you got stuck. I'll see you soon. Okay, welcome back. Hopefully you have the answer of 2 mole. I'm just going to talk through this one quickly in case you got stuck and show you what I did. So from the question, it's asking us to find the number of mole of carbon dioxide, and we have been given the number of mole of butane. But meaning 4 carbons, ane meaning alkane, all single bonds. So we have CnH2n plus 2 again, so C4H10. And again, we have complete combustion. So step 1 is to balance our complete combustion equation. It wasn't given this time. So we start off with C4H10 gas plus O2 gas going to CO2 gas and H2O. Then I always start by balancing my carbons. So we have C4 on the left-hand side, which means we will have 4 CO2 on the right-hand side because the carbon can only go to CO2. Then I'm going to take my number of hydrogens, divide by 2, and make that the coefficient of the water. So H10 becomes 5H2O. When I add this up, I get 5 oxygens from the water and then 8 from the CO2, which means I need 13 oxygen atoms. So that's going to be 13 on 2 O2 molecules. Okay, so I'm going to take that 13 and divide by 2. It's an odd number, so to get rid of that, that means I'm going to have to multiply everything by 2. So I'm going to end up with a coefficient of 2 in front of my fuel. So I just multiply everything by 2, so I get 2 C4H10 plus 13 O2, because I'm going to get rid of that 2 mathematically, 8 CO2 and 10 H2O. Now I can work out my stoichiometry and my mole ratio. So I was given the number of mole of butane. Pay attention to the significant figures in the values that you were given. This is 0.50, and this guy's important for our sig figs. Now I'm going to go to the coefficients. So the coefficient of what I want, which is CO2, is 8 in our balanced equation. So that goes on top, and I'm going to divide by the coefficient of what I know, which is butane. So that's going to be 8/2 multiplied by the number of mole of butane of what I know. So that means that number of mole of CO2 is going to equal to 8/2, which is 4 times 0.50. We will end up with a total of 2.0 mole to an answer correct to 2 significant figures. Okay, hopefully that one seemed pretty straightforward. Let's look at our next type of question. So you may remember, hopefully you do, that you have a number of calculations available for working out the number of mole. We have mass of substance, which is where we do mass-mass stoichiometry, or any time we want to go between mole and grams or grams and mole, we're going to be using this equation. We have M is equal to N times MR, or large M, where we want to go between molar mass and number of mole. We have the known gas at SLC Okay, so this is using our molar volume equation. The number of mole is equal to V on Vm, remembering that we just have one value of Vm in our data booklet. Unless a question provides us with a different one, we can still use that equation. And then we have the ideal gas equation, which when we convert that around from PV equals nRT, we get N is equal to PV on RT. Okay, then we also have these rearranged for volume. It is very common that you will need to be able to find the volume of the gas from a given situation in a question. Remembering also that we can convert pressures and volumes to different units, and that we must have our pressure in kilopascals for this equation. Our volume must be in liters. R is going to be 8.31 from our data booklet, and temperature must always be in Kelvin when we're dealing with gas. So let's have a look at this one. This is a mass-mass stoichiometric problem again. So we're going to be using our N is equal to M on M or MR, depending on which one you used. This time we've been asked to calculate the mass, so we're going to be aiming for grams of carbon dioxide, and we need to convert through to kilograms in the final question. Okay, so the question's asking us to give it in kilograms. When 540 grams of propane, again C3H8, is burned completely in oxygen. So here's our combustion equation for propane that we saw earlier. Now we need to work out the number of mole of propane. So we're going to take the mass from the question, 540 grams of propane, divided by the molar mass of propane. This comes from 3 times 12 plus 8 times 1 for working out the molar mass, which is going to be 44 grams per mole. That gives us 12.3 mole of propane. Our mole ratio is going to be the same as it was in the previous example because we're using the complete combustion of propane again, so that is not going to change. I will have 3 CO2 for every 1 propane that is burnt. That means if I multiply that ratio by the number of mole of propane, I have 36.8 mole of CO2 being produced. However, the question wants us to give this in a mass value. So we're going to multiply here by the molar mass of CO2, which funnily enough happens to be the same as the molar mass of propane. This one coming from 12 plus 2 lots of 16 from the oxygen, which again is 44. This means that we will end up with 1,620 grams, and then we need to convert through to the correct unit as specified in the question and watch significant figures. So we're going to divide by 1,000, 1, 2, 3, and then we're going to report in only 3 significant figures for our answer. Okay, same thing as before. Now it's your turn, so pause your video, have a go at this question and the key questions from the textbook if you haven't done them yet, and I will see you when you come back to check your answer. Okay, so welcome back. If you got stuck on this one and want to listen to me talking through, you can follow along. Otherwise, just skip forward to the answer and check your answer and continue on. Okay, so as with before, we are dealing with trying to find the mass of carbon dioxide, this time from 3.6 kilograms of butane. So we're going to need to convert this to grams before we can use it in our formula. We've been given the formula for butane, so that means we can find the molar mass, and we're dealing with complete combustion. So we can just use the combustion equation that we had before, that we balanced in the previous question. Okay, so I'm just going to write that out here. So this is just our 2 butane reacting with 13 O2 to give us 8 CO2. So we can now determine the number of mole of butane. Okay, so this guy here, and we know that we've got 3.6 kilograms, so we're going to have 3.60 times 10 to the 3, because I'm just going to multiply by 1,000 to convert that to grams, and then we're going to need to know 4 times 12 plus 10 times 1, for our molar mass, which is going to give us 3,600 grams divided by 58 grams per mole for the butane. So we will have 62.0629, oh sorry, 69, let's lose that mole 2 there, 69 mole of butane. Remember to use unrounded values in your calculations until you get to the final answer. So now I need to work out my number of mole of carbon dioxide based on my number of mole of butane. So we know from before that this is going to be an 8:2 ratio or a 4 ratio multiplied by the number of mole of butane, which is going to be 62.069, which is going to give us a total of 248.276 mole. We can't stop here though, because the question wants us to find the mass of carbon dioxide. So now to find the mass of carbon dioxide, we're going to use N times big M, or MR, which is going to be our number of mole, 248.276, multiplied by 44 grams per mole, which is the molar mass of carbon dioxide. This is going to give us a very large number of grams, 10924.138 grams. Okay, but we need to get this to 3 significant figures. So we can do that by using scientific notation. So we're going to take it to 3 significant figures. Will give us 1.09 times 10 to the negative 4, grams. Or we could do this as 10 to the 0.9 kilograms. Either would be acceptable because the question has not specified what unit the mass must be given in. So all you really want to do is make sure you have it in the right number of significant figures. All of these questions should be just revision for stoichiometry. So if you're finding them easy, that's fantastic. Continue on with your chapter questions. And next up, we're going to do a quick review of volume stoichiometry. Okay, so with our volume stoichiometry, we're using our volumes of our gases. So we start to see our volume equations and gas equations coming in. These are the new ones to us this year. Okay, so this looks at the volumes usually of oxygen required to burn the fuel, or the volume of gases that are produced during the combustion. The standard lab conditions as given in our data booklet are 25 degrees C. Remember, this is 298 Kelvin and 100 kilopascals. Under those conditions of SLC, the molar volume of a gas, i.e. 1 mole of gas, will occupy 24.8 litres. So we can determine the number of mole we have by taking the volume present and dividing by the volume for 1 mole, which gives us this equation here. For non-standard conditions, i.e. for a specific instant in time where the pressure may be different or the temperature may be different, we're going to use PV equals nRT. And our pressure must be in kilopascals, temperature in Kelvin, and we're going to use the value of the gas constant as 8.31 joules per Kelvin per mole. All of these, remember, are in your data booklet. So the first example that we're looking at with this one is we're looking at mass volume stoichiometric calculations at standard laboratory conditions. Okay, so it's told us straight away that we are at SLC. We want to find the volume of carbon dioxide. So we want to find V of CO2 in litres, produced when 2 kilograms of propane is burned completely in oxygen. Again, we have complete combustion. We're going to need our balanced chemical equation, same one as before. We need to find the number of mole of propane. This has been given to us as a mass. We need to convert to grams to be able to put it into the equation. So we're going to convert this to grams and then divide by the molar mass. So we're going to use our N is equal to M on the molar mass. 2,000 grams divided by 44 grams per mole is going to give us 45.5 mole. Then we want our mole ratio, And as we had before, the number of mole of CO2, which is what we want, over what we know, 1 mole of propane, is giving us a 3:1 ratio. So to find the number of mole of CO2, we're going to multiply by that ratio times the number of mole of propane, which gives us 136 mole of carbon dioxide. Now we've been asked to find the volume. This time, because it's a SLC, we can use the volume is equal to N times Vm, where Vm is going to be 24.8 from our data booklet. When we do that, we get 136 mole multiplied by 24.8 gives us 3,382 litres. Again, 3 significant figures, so this is 3.38 times 10 to the 3 litres, remembering to use a capital L for your unit here. Okay, your turn now. Next one. Again, we're looking at our butane, so we're just using the same combustion equation as we did before. You're looking for the volume of carbon dioxide produced when we burn 300 grams of butane. Have a go, then come back and check the answer. Okay, so hopefully you got this far. We're using the same combustion equation again. We've worked out our number of mole of butane using the mass from the question, 300 grams, so no conversion needed here this time, divided by the molar mass of butane, which gives us 5.172 mole of butane. A number of mole of CO2 is given by the mole ratio 8/2, multiplied by the number of mole of butane, giving us a total of 20.69 mole of CO2. Now we just want to plug this into our new equation that we're using, which is N is equal to V on Vm. We want to rearrange to find the volume. So this being V of CO2 is going to equal N times Vm. Substitute in the values from the question that we have, 20.69 multiplied by Vm from the data booklet, which is 24.8, and we end up with a total of 513 litres of CO2 being produced. So that one should be nice and straightforward. It's just remembering to use that N is equal to V on Vm equation. This time we're going to do non-standard conditions, so we're looking at the PV equals nRT arrangement. Okay, so again the question is being nice, it's giving us propane. We know the combustion of propane equation pretty well by now. Then we've been told we have 800 grams of propane, so this is the mass of propane. So we're going to take 800 divided by 44, gives us the number of mole of propane. Our mole ratio is 3/1 as it was in the previous examples. And then this time we're going to multiply by 18.2, giving us a total of 54.5 mole of CO2 being produced. Now, because we don't have SLC, we're using PV equals nRT, we need to find the pressure and various other conditions from the question. So we were told that the pressure was 200 kPa, so pressure is 200 kilopascals. That is in the correct unit, so we can substitute that straight in. V is what we're looking for. N we have as 54.5, but temperature is equal to 60 degrees C. We can't substitute that in without converting to Kelvin. So we're going to have 60 plus 273 to convert to Kelvin, which is going to give us 333 Kelvin. Now we can just substitute in after rearranging our equation to get V is equal to nRT on P, because we're going to divide both sides by P. When we substitute those in, we get 54.5 for N, 8.31 for our ideal gas constant, 333 being our temperature in Kelvin divided by the pressure, which gives us a total of 755 litres. With these questions, it's always a matter of just substituting in the values from the question, making sure before you do that each one is in the correct units. Okay, your turn. Make sure you check all those units and then come back and check your answer. Okay, so this is our question pulled apart. We can see that we're after the volume of CO2 again. We've been given a mass of butane, this time in kilograms, so we're going to have to calculate mole and convert to grams before we do. Butane will have the same formula as it did before, C4H10. We've been given the gas. We want to find the gas volume is what we're looking for at 40 degrees C and 400 kPa. So this is not at standard conditions. So we're going to have to use PV equals nRT. So let's get started. First thing we need to do is work out, since we want to find the volume of CO2, we want to work out our N of CO2. So we need to find the N of butane first, which is going to be our 5.00 times 10 to the 3 divided by 58, which is going to give us 86.2 mole. Our mole ratio, our N of CO2, is going to be 4 times our N of butane. We know these from our previous questions that we've dealt with butane. So we get 4 times 86.2, which is going to give us a total of 344.83 mole. You will notice in these combustion questions, because we're generally talking about production of energy on a societal scale, these numbers start to get quite large. We're talking about burning kilograms or multiple liters of fuel. So don't freak out if these numbers are starting to get much larger than what you've used to dealing with in year 11, where we dealt with 2 mole or 9 mole. We will see questions in year 12 where we're seeing multiple mole up in the hundreds or higher, because we're talking about dealing with energy on a much larger scale. Okay, so now that we've got that, we need to use PV equals nRT. We have a pressure that is 400 kPa. That one's okay. Volume is what I'm looking for. N is 344.83. R is equal to 8.31 from our data booklet, and T is equal to 313 Kelvin, and that's because up here I already did the conversion where I added 273 to go from Celsius to Kelvin. So when we substitute that in, we get V. So we had PV equals nRT, so we're going to have V is equal to nRT on P, which is going to be 344.83 multiplied by 8.31 multiplied by our temperature, which was 313 Kelvin, all divided by our pressure, 400. When we plug that into our calculator, you should end up with 2,242.28 litres. Again, watching our significant figures, so we're going to report this in 3 significant figures. 2.24 times 1, 2, 3, 10 to the 3 litres will be our final answer. Another question, this time we're looking at gas volume calculations. This is remembering that irrespective of the type of gas, gas will occupy the same volume if they are at the same temperature and pressure. It doesn't matter what they are. So for this one, we're looking at the burning of methane. We have the balanced chemical equation for the combustion of methane, and we're asked if 50 ml of methane is burned, so we're burning 50 milliliters of methane here. Calculate the volume of O2 gas required for complete combustion at constant temperature and pressure. So this one here is what we're looking for. It doesn't matter, it doesn't have to be standard temperature and pressure, just the temperature and the pressure are not changing. So if it's constant temperature and pressure, then the volume ratios are equal to mole ratios. Okay, so we look at our mole ratios and we can see that for every 1 mole of methane, 2 mole of oxygen gas is used. So it's a 1:2 ratio. So if I have 50 mil, then X here, 2 times 50 is going to equal 1 times x, which is going to be 100 is equal to x, x being the volume of O2. This is because 1 volume of CH4 reacts with 2 volumes of O2. And from the question, 1 volume was equal to 50 milliliters. So that means 2 volumes is going to be 2 times 50 milliliters. This one seems a little unusual at first, but it really is as simple as it seems. Don't try and overcomplicate these questions. So here's your one for you to pause the video and have a go at yourself to see if you have worked out this answer. Okay, now it's asking us, you've got 50 ml of methane being burned in air, calculate the volume of CO2. So not O2 this time, CO2. Come back and see the answer. Okay, hopefully you had a go at this yourself. If you're a little bit confused, let's have a look at it. What we're looking at here is we have a 1 is to 2 is to 1 is to 2 ratio. So if 50 mils of methane is reacting, it will produce 50 mils of CO2. Okay, because there are 1 is to 1 ratio. So in this case, all we're saying is that if 50 milliliters of methane is burnt, it will produce 1/1 times that, which is 50 milliliters of CO2. Hopefully you worked that one out. Whew. Okay, this one's going for a long time. I will put breaks in this, but let's get through all these types of calculations. Okay, now we're looking at limiting reactions. It says extension, but really you should be familiar with limiting reactants and working out limiting and excess. If you're not, make sure to go back and watch those videos from year 11. I'll put a link to them later on so that you can review these. In this case, when we're talking about limiting and excess, we're going to be usually talking about incomplete combustion. Okay, so if we have a look here, calculate the volume of carbon dioxide in litres produced when 65 grams of butane is burned completely and 200 litres of oxygen. The gas volume is measured at SLC. The equation for the reaction is given below. So we know that we're at SLC. We know if 65 grams of butane has been burnt completely, then we essentially know that CH4 is going to have to be the limiting reactant. Otherwise, we wouldn't have complete combustion. If oxygen was limiting, then we would have incomplete combustion. But we can work this out, remember, by working out the 65 grams of butane. Okay. So we're going to have N of butane. Remember, in these ones, you will always have the ability to work out the both number of mole. So you won't have a situation where there's only one number of mole being able to be calculated. You'll be able to work both number of mole for the reactants. And this is a key indicator that you have a limiting and excess situation if the question hasn't specified that. So we're going to get 1.12 mole of butane, okay, and 200 litres of oxygen. So N of oxygen is going to be V on Vm, because we're told we're at SLC. Okay, now we have both number of moles. We need to work out our limiting and excess. So N of O2 required for 1.12 mole is going to be 13, what I want, over what I've got, 2 times the number of mole of butane. So this is just assuming I don't know how much O2 I have. I'm just going based on this amount of butane, how much oxygen would I need for complete combustion? So if we take our 13 divided by 2 and multiply that by 1.12, we get 7.28 mole. And that's what's required. If we have a look over here, 8.06 is greater than 7.28. Therefore, oxygen is in excess because I have more than is needed by this reaction. And what is the volume of carbon dioxide formed? Part B, remember this must be based on the limiting. So this will be based on the number of mole of butane. So N of carbon dioxide, let me put this one up here, N of CO2 is our 8 on 2 times 1.12. So we're going to have 4 times 1.12, which is going to be 4.48 mole. And then the volume of CO2 is going to be 4.48 multiplied by our molar volume, 24.8, equals 111.1 litres, or 111 litres, to 3 significant figures. Okay, so this is just using exactly the same kinds of limiting and excess that we saw in year 11, now just combining them with our new gas equations. And you can use your knowledge of combustion reactions to kind of try and help you, because in the case of complete combustion, oxygen can never be the limiting reactant. We can have exactly the enough, but for complete combustion, we must have excess oxygen. So that's a really good thing to look out for in your questions. I'm actually going to leave this one here and then do a second video on gas calculations involving thermochemical equations, which is the last bit, because this one is massive. Hopefully you have only watched the bits that you need in order to revise and feel more confident about your stoichiometry. Remember, if at any time you're unsure, just send me a message and I'm happy to go through questions with you. So we'll leave this one here. When I put this up, I will make sure I put timestamps in for each of the different types of calculations. I hope that you are feeling confident, and I will see you in class.